So, hello everyone, welcome to the 10th live session. And today we are going to continue our discussion regarding the MOS problems. And as previously, as someone had mentioned, to solve the problems related to the previous assignment about this MOS cap only. So, we will be solving some of the assignment problems since the deadline is over for that assignment. So, the problems they had sent me, I will be solving those first. So let's start today's session. Okay, so I guess there is a mistake over here. Today is 29th, so let me correct it. I by mistake wrote yesterday's date. So let's begin today's session. So first of all, there was one problem left from the previous assignment that I had um, posted in the previous live session. So let's begin with that problem, and this is more associated with the MOS cap that you must have been seeing till now. So it says that we have to consider a MOS cap with p-type silicon substrate. So it is doped with a concentration of acceptor concentration of 10 to the power of 14, and the oxide is silicon dioxide with a thickness of 50 nanometers, and the metal semiconductor work function is given to be minus 0.83, and the thermal voltage and the intrinsic carrier concentration are given, and as a result of this thing we need to find the threshold voltage of this MOSFET. Okay, so let's start this solution for this problem. As we know, the VT, sorry, the VTH, which is the threshold voltage, is simply given by phi ms. Actually, it is VFB, but since we are considering the oxide to be charge free, as a result of this thing, we will take it to be just phi ms because the oxide is charge free. Otherwise, we had to take it phi ms minus q ox prime by c ox prime. Okay, by prime I mean the oxide charge, the oxide capacitance, and the oxide charge per unit area. Okay, so phi ms plus, actually it is phi s plus gamma root phi s, but the thing is we are considering the surface potential to be pinned at 2 phi f, but in the previous class you must have seen the all the discussion was about that this pinning does not happen at 2 phi f, it happens at some 2 phi f plus some delta phi. Okay, that delta phi was given by was approximately 4 to 6 times the thermal voltage. Okay, so this is q dep prime by c ox prime. So q dep prime is simply q times na into xt max. Okay, so we are considering the maximum depletion width. Okay, so I should have put in brackets. Okay, so the maximum depletion width is xt max, and we have to consider the Fermi level pinning, sorry, the surface potential, not the Fermi level pinning. I'm really sorry for this. We consider the surface potential to be pinned at 2 phi f. Okay, this is the classical thing. Okay, so from this, first of all we need the value of phi f. Phi f is simply phi t ln of Na by Ni. Okay, so it is simply 25.9 millivolts ln of Na is 10 to the power of 14 by Ni. Ni is 1.5 into 10 to the power of 10. So if we solve for this, we will get the value of phi f to be equal to, let's solve for this, it is ln of divided by 5 into 25.9, so it is 0.228 volts. Okay, so this is the value of the phi f, and from this we can find the depletion width, maximum depletion width, to be equal to xt max equal to 2 times epsilon s is simply relative dielectric constant of this silicon, 11.7 times 8.85 into 10 to the power of minus 14 times 2 times phi f. Phi f came out to be equal to 0.228 divided by q times Na. Q is 1.6 into 10 to the power of minus 19 and Na is 10 to the power of 14. This whole thing under the square root. So let's find out the value for this. So it is 2 times 11.7 times 8.85 times 2 times 0.228 6. So it's 590 under root. So it's 24.29 into 10 to the power of minus 5 centimeter. So this is the maximum depletion rate. So from this we can find the Q depth, which is a depletion charge per unit area, which is Q times Na times Xt. Q is simply 1.6 into 10 to the power of minus 19. Na is 10 to the power of 14. And Xd is simply 24.29 into 10 to the power of minus 5. So let me solve for this. Okay. So it's coming out to be equal to 38.864 into 10 to the power of minus 10 coulomb per centimeter square. Okay. Now Vt is simply, V threshold is simply phi ms. Phi ms is minus 0.83 plus 2 times phi f, which is simply plus 2 times phi f is 0.228 plus q depth by Cox. Okay, q depth by Cox is simply 38.864 into 10 to the power of minus 10 divided by this Cox is epsilon ox by Tox. Let me write down the value of epsilon ox. So it is 8.85 into 10 to the power of minus 14. Tox is simply 50 nanometer. So it is 50 into 10 to the power of minus 7 centimeter. So let's solve for this. So it is, this thing is simply minus 0.374 plus it is 38.864 into 50 divided by 5. So it's approximately 0.056. Okay, so let us subtract this 0.374 plus 0.0563. So it's coming out to be equal to minus 0.3. Okay, so option A is the correct option to go with. Now, this is the problem associated to the assignment itself. Okay, you must have seen this in this year's assignment, and someone had mentioned to try to solve this problem. So let us analyze this problem first. So this problem says that which of the following options correctly depicts the variation of the depletion in width inside a semiconductor with respect to the applied potential, that is VGB. Okay, that is between gate and body. Okay, and we have been given the threshold voltage some VT and VFB, which are given in the plot. Okay, so first of all, we know we have to look into the relation of this. How does this psi s change with the VGB first? Okay, so there is certain uh, uh, you can say a relation between this VGB and this psi s. Okay, so if we now solve for that VGB psi s relation, we will get a relation uh, which will be something like this: VGB is equal to VFB plus psi s plus gamma root of psi s plus phi t exponential of psi s minus 2 phi f by. Okay, so the relation looks like this. So how did we arrive at this relation? So it is simple. We started with VGB. Similar is the threshold voltage condition now. Okay, whenever we find we go for this threshold voltage, we say that VT is equal to VFB plus psi s plus gamma root psi s. Okay, that's considering the classical model. Okay, if we consider the classical model, we go by this. Okay, so VGB is the potential drop across the gate body, and it will be, this whole potential will be dropped across the semiconductor, across the what you can say oxide. Okay, and across the what you can say okay, across the oxide. Okay, let me not use prime notations over here. Okay, we know that this phi ms is simply VFB plus Q ox prime by C ox prime. Okay, this we had done previously. Okay, I had showed the relation how the flat band voltage is governed by two factors. One was the metal semiconductor work function and other was the oxide charge. Okay, so flat band voltage is like this. So we can simply see that VGB is VFB plus Q ox prime by C ox prime plus psi s plus psi ox. Okay, this is simple. Now we know that the gate charge will have a relation using the Gauss law. Okay, with the oxide capacitance, which is simply this Qg prime will be simply equal to, you can say, C ox prime times the psi ox. From this we can simply get VFB, okay, to be equal to Qox prime by Cox prime plus Qg prime by Cox prime plus psi s. Okay. Now we know the total charge on the gate will be reflected at two positions. Okay, will be reflected at two positions, which is simply the total charge, which is the oxide charge, plus the gate charge, plus the semiconductor charge, which is inside the semiconducting channel, has to be equal to 0. Okay, because overall this is neutral. Okay, charge neutral. So you can clearly see that Qox prime plus Qg prime is simply minus times Qs prime. Okay, it's as simple as that. So it is simply now VFB plus psi s times plus times minus Qs prime by Cox prime. Okay, I guess I am doing it correctly. Yes, yes. I have added these two quantities. Okay, okay. Now, in the previous live session, we solved for this Qs prime. Okay, we solved for this semiconductor charge, and from that semiconductor charge, we found out the inversion charge using the charge sheet approximation. Okay, so you can clearly say that this Qs, which we found out in the previous lecture, it came out to be, we solved for the Poisson equation. I guess you all must remember that we found out that this Qs, it came out to be equal to minus times to Q epsilon s and a square root, okay, times the psi s plus phi t exponential of psi s minus 2 phi f by phi t. This whole thing was raised to the power of 1 by half. Okay, now if we substitute this Qs here, you will get this expression. Okay, you will get this expression. Okay, now the issue is we have a problem in hand, that we have to find how does this psi s vary with the uh, how does this psi s vary with the applied bias, that is V. Okay, so this is psi s and this is applied VGB, which is the gate body bias. So if we carefully look at this relation, you can say that this psi s, it just we just started from the flat band voltage. Okay, so there is this actually this is transcendental in nature. Okay, so you cannot solve for this like you can say that if I have a value of VGB, I can get psi s value. It's round way. Okay, it's actually the opposite way. It is that if I have a value of psi s, I can know the VGB. Okay, this equation is like that because this has a linear function over here, and there is a square root function of psi s also in the second term. So the issue now is that this is kind of a transcendental, and we now know we have to use some approximations in order to arrive at some value. Okay, now if I draw this psi s versus VGB, this will be our VGB, okay, or the applied bias, and this will be our psi s. Okay, if this is our psi s and this is our VGB, and we start at some flat band voltage, let us say this is our flat band voltage. We know that at flat band psi s is equal to 0. Okay, so the whole thing over here is just equal to 0 and VGB is equal to VFB at psi s equal to 0. So this is at psi s equal to 0, we are here at VFB. Now as this value of this VGB increases, we enter the depletion region. Okay, so this psi s is still less than 2 phi f. Okay, psi s is still less than 2 phi f. Now if we are in depletion region, so let me write it like this, that if we are in depletion region, psi s is less than 2 phi f. Okay, and this whole expression over here, it will be somewhat kind of a linear function. Okay, it would be somewhat of a linear function of this uh, phi of this psi. Okay, when this is less than phi f, but not completely linear, because there is a square root dependence of psi s as well. So it will look like something this. And after that, after 2 phi f, let me write clearly, if this is our phi f, okay, and if this is our 2 phi f, you can see this psi s is still increasing a bit. Okay, and it saturates at some value which is phi 0. Okay, this is some value, this is 2 phi f, and this is some value which is phi 0. So you can clearly see that this relation initially is kind of a linear, and then it saturates also, so this is a simple demarcation for this the regions of operation as well. Like this will be our depletion region of operation, this will be our weak inversion. Okay, and although this is exaggerated, this is not that much large, I'm sorry for this, so it will be moderate inversion kind of a thing, what we studied previously. And now this whole thing will be strong inversion. Okay, this whole thing will be strong inversion. So you can see from here that as the value of VGB is increasing, the value of psi s is also increasing, and initially when the depletion charge is being built up, it is somewhat linear in function. So the problem with us was the problem in hand with us was that how does this depletion width change with the bias. Okay, so it is now simple. How does it change? It changes as we know, this depletion width, it has this square root dependence on psi s. Okay, xd, it has a square root dependence on psi s, and initially you can see that VGB is almost having linear dependence in depletion mode of operation, and then it saturates, and it is not completely linear. You can say that it has the effect of the square root as well, square root psi s, but for these are just the we can say repercussions of considering the moderate inversion, since we have dealt with it in a real depth. So that's why you can see this dip kind of a thing over here. Okay, and you can clearly see that this psi s now which is having some relation with this xt, and it is kind of a square root dependence in the depletion region. So the graph will look simply, the graph for this will simply, for this depletion width xt with the bias, will simply look like this, that initially it will have a somewhat square root dependence. Okay, so initially it will be increasing, the depletion width will be increasing from VFB, and after VT, which is the threshold voltage, we will be having almost the saturation of this depletion width. The saturation is there because the surface potential has saturated with respect to the VGB, that is the applied bias. Okay, that's what this plot over here, I guess this plot, yes, this plot shows here, that as the depletion width, as we increase the bias, there is pinning of the surface potential, and as the surface potential is pinned, we have this relation, that this there is almost this square root kind of a dependence of this depletion width with this is, and after the surface potential is pinned, it is constant kind of a thing. Okay, this depletion width is now constant. So that's all about this problem, which was asked in this year's assignment, uh, and we have solved it hopefully after the deadline. Now there is this other problem, okay, which is which was also asked in this year's assignment, and it says that we have this MOS cap again, and this MOS cap is having p-type silicon semiconductor uh, as its substrate, and the thickness of the insulator is 100 nanometer, and also uh, we have been given the uh, that the gate is made of aluminium. Okay, it's NiUm, and the gate is made of aluminum, and the work function of the gate is given to be equal to 4.2 electron volts, and the band gap of the silicon, which is 1.12, and the electron affinity, they are both given. We have been provided the intrinsic carrier concentration as well, and the CV characterization is performed for the threshold voltage measurement. Okay, and we are getting two threshold voltages. One is VT1 for the concentration of 10 to the power of 18, and another measurement was performed on a different MOS capacitor, okay, whose substrate doping is 10 to the power of 16, and rest all the parameters were similar. Okay, so the thing is, uh, everything is similar except that the substrate doping. So we have been told to find the difference in the threshold voltages measured and the direction, how does the CV change. Okay, and also the electronic and the hole mass, they are both effective masses, they are both given to be equal to what you can say, they are both given to be equal to same. Okay, they are both same. So this is again the problem related to the threshold voltage. So let us use the relation for the threshold voltage considering the pinning happening at 2 phi f. Okay, we have to take the classical definition of the pinning again. So for the ease of calculation, okay, so let us go for this. So it is for the this CV measurement 1, there is this VT1 phi ms1 plus 2 phi f1 plus q dep max 1, okay, by c ox prime. Okay, so this phi f is simply phi t, we have been doing it for long now, ln of na1 by ni, and this phi t is simply 26 millivolts, it's 0.026, ln of na1 is 10 to the power of 18, it is 10 to the power of 18, and ni is 10 to the power of 10. Okay, so let's solve for this. Ln of 10 to the power of 8, sorry, ln of 10 to the power of 8 into 0.026, it is 0.48. Okay, sorry, what is happening with this thing? It is 0.48 volts. This is phi f1. Okay, now from this we can find this maximum depletion width, and this maximum depletion width is simply xt max 1 is simply 2 times epsilon s 2 phi f1 by q n a. Okay, we have to consider the Fermi level, the surface potential to be pinned at 2 phi. Okay, so it is xt max, and q depth is simply equal to q times na1 times xt max 1. Okay, so it will be simply this q depth is simply equal to 2 times epsilon s q times na1 times 2 phi f square root. Okay, so it is simply 2 times 11.7 8.85 into 10 to the power of minus 14 times 1.6 into 10 to the power of minus 19, and a1 is 10 to the power of 18. Okay, and 2 times phi f is 0.48. All this under the square root. Okay, let me write it here. Okay, so let us solve for this. 2 times 11.7 times 8.85 times 1.6 into 2 times 0.48, so under root it comes out to be equal to 5.64 into 10 to the power of 7 coulomb per centimeter square. Okay, this is for q depth 1. Now vt2 for threshold voltage. For the second case, we need to find out phi f2. Phi f2 is simply phi t ln of na2 by ni, and it is 0.026. Ln of na2 is simply 10 to the power of 16. It is 10 to the power of 16 divided by 10 to the power of 10. So let me calculate this value. 1 of 10 to the power of 6, 0.026, it is 0.36. Okay, so this is the value of phi f2. So the q depth 2, will simply be 2 times epsilon s q times na2, it should be 2 phi f1, 2 phi f2, 2 times 11.7, okay, times 8.85 to 10 to the power of minus 14 into 0.6 into 10 to the power of minus 19 times Na is 10 to the power of 16. Okay, Na2 and 10 to the power of 16 and this 2 phi f is 2 times 0.6 raised power 1. So let's calculate the value for this. It is 2 into 11.7 times 45. So it's 4.88 into 10 to the power of minus 8 coulomb per centimeter square. Now uh, there is this important thing. Now we have to subtract the two voltages, that is Vt1 minus Vt2 is equal to phi ms1 plus 2 phi f1 plus q dep 1 by C ox prime. Since the oxide thickness is same, minus times phi ms2 minus 2 phi f2 minus q dep 2 by C ox prime. Now let's be careful about this metal semiconductor work function. I myself did this mistake while solving this, and I was not able to get the option correctly once. So one of my friend, he was there with me, and he pointed out that I am missing on this semiconductor work function. Okay, so what I had done previously, uh, uh, I had done is that I had cancelled both the phi ms. I didn't realize that the doping is different. Okay, since the doping is different, what happens is, you can see over this figure, if the doping is different, the difference between EI and EF is different. Okay, so they there will be different semiconductor work function. Okay, so it is simple. So when this doping is different, the semiconductor work function will not be same. So what happens is simply, this is phi m, since the metal is same for both the materials, this is phi m minus phi s1, okay, plus 2 phi f1 plus q dep 1 by C ox prime, okay, minus phi m2, but phi m2 is same as phi m1, okay, plus phi s2 minus 2 phi f2 minus q dep 2 prime by C ox prime. Okay, now this psi s1 is simply equal to, it will simply be equal to chi, which is the electron affinity. Let us go back to this diagram. It will be simply equal to chi, this is our chi, this is our Eg by 2, okay, and this is our phi f, okay. So this psi s will be simply chi plus Eg by 2 plus phi f1, okay, and psi s2 will simply be chi plus Eg by 2 plus phi f2. So what is happening now? If I substitute this psi s1 and psi s2 in the above expression, we will be having this psi s, this Eg cancelling out, okay, and we will be left with minus phi f1 plus 2 times phi f1 minus, and it will be plus, then it will be plus phi f2 minus 2 phi f2 plus q dep 1 prime minus q dep 2, sorry, q dep 2 should be as the subscript, okay, q dep 2 prime by C ox prime, okay. So it will be simply phi f1 minus phi f2 plus q dep prime 1 minus q dep 2 prime divided by Cox prime. So I am doing this solution in the detailed manner because someone had asked over email to do it in a detailed manner. Okay, so that's why I am doing all these solutions for all these three problems in a detailed manner. Okay, so this is our now let's substitute the values. Okay, so phi f1 was phi f1 was 0.48 and phi f2 is 0.36. So it is 0.48 minus 0.36 plus Cox is simply epsilon ox by Tox, and Tox is 100 angstroms. Okay, if it's 100 angstrom, it means it is 10 nanometer. So it is 10 to the power of minus 10 times 10 to the power of minus 9. So it is 10 times 10 to the power of minus 7, or it's 10 to the power of minus 6 centimeters simply. 10 to the power of minus 6 simply. And this is epsilon ox by d ox, so it is 3.9 into 8.85 into 10 to the power of minus 14 times q dep 1. Okay, q dep 1 is 5.64 minus it is 0.488. Okay, 0.488 into 10 to the power of minus 7. Okay, so let us calculate it again. So it will be 5.64 minus 0.488, 5.152 divided by 3.9 divided by 8.85. It is okay, 8.85 times 10. It is 1.492. It is 1.492, and this thing is 0.48 minus 0.36. It is 0.12 plus 0.149 plus, sorry, oh, I guess I am doing something. Okay, 0.492, so it is 1.612 volts. So this is the shift in the voltage. Okay, so it is this one. So we have to select among these two options. Okay, whether it's right or left. Okay, so when the doping decreased, the threshold voltage was less. Okay, so the threshold voltage, since the threshold voltage is less for the less doping case, it means that the CV curve has shifted to the left, because now the device is able to turn on at a less gate to body bias as compared to the case when we have high we can say substrate doping. Okay, so the option C, which is written over here in green, is the correct one. Okay, so now moving to another problem of the assignment that we have solved, that you have solved in this week's live session. Sorry, in this in the MOSCAP's um, assignment section. So this problem is also associated with MOSCAP, but now it is having some additional, instead of the silicon, it is having a channel which belongs to kind of a oxide kind of a thing. Okay, you can see that this is oxide semiconductor like ZNO. Okay, so this is n-type material, some n-type material, oxide semiconductor, and we have been given the relative permittivity values. Okay, the relative permittivity values and the band gap of this material, this is ZNO, and we have been told that this material is currently operating in the depletion mode, and the substrate concentration is 2 into 10 to the power 16, and the silicon dioxide, which is oxide, thickness is 150 nanometer, and it is relative permittivity is 4, and it is deposited on the top of this ZNO, and the surface potential is zero point 0.8 volts. Now we have to calculate the electric field intensity, okay, and the semiconductor across this oxide and the semiconductor. Okay, so let us sorry, what has happened to this? Okay, so let us start this problem by analyzing the how does this electric field uh, uh, vary uh, inside the ZNO. Okay, so if this SiO2 is the oxide, then there will be this field drop across the oxide. Okay, and we will be having some drop across the semiconductor, which will look like this. Okay, sorry, so it will look like this. The electric field will terminate at some point inside this ZNO, and this will be our other terminal, and this will be our first gate terminal. Okay, if this is our epsilon ox, and this is our epsilon sorry, electric field E of ZNO, then what we have to find out is the, if this is our depletion width, we have to find out the electric field, peak electric field, which is the is at the interface. Okay, the electric field intensity will be obviously at the maximum at the interface. Okay, so it will be like this, and you can see clearly this is a kind of a uh, uh, triangle thing, and you can clearly say that it will be having this surface potential will, which is given by the area of this electric field curve. Okay, with respect to the position, as you know, if we solve for this the Poisson's equation, you must have seen that minus d psi by dx is equal to E. Okay, yes, minus d psi by dx. Okay, so when you integrate this electric field with respect to the position, you will get the potential. Okay, so the potential at the surface will simply be equal to psi s, and it will be equal to the area of this triangle, which is 1/2 of the base is xt times the peak electric field. Okay, so what do we need to find out? We need to find out the depletion width. So the depletion width has a square root dependence on psi, and it is simply given by 2 times epsilon s, here is for this ZNO, okay, times psi s divided by q times n. So it's 2 times ZNO has this relative dielectric constant, there is a relative permittivity of 8.5 times 8.85 into 10 to the power of minus 14 times psi s is 0.8. Okay, so it's 0.8 divided by QNA, which is 1.6 10 to the power of minus 19 times Na is 2 into 10 to the power of 16. So let's calculate the value for this. Okay, so it comes out to be between, sorry, there was some error. So it comes out to be equal to 1.94 into 10 to the power of minus 5 centimeter. So it is the depletion rate. Okay, now we have got this. We can calculate the value of the field, which will be 2 times psi s by xt. It is simply electric field in the Zn, the peak electric field. Okay, it is 2 times psi s is 0.8, xt is 1.94 into 10 to the power of minus 5, so it will be 10 to the power of 5 volt per centimeter, so it's 1.6, so it's 1.6 divided by 1.94, so it's 0.829 10 to the power of 5. Okay, okay, so it's 0.83 kind of a thing. Okay, now we know that to maintain the continuity, the epsilon s, sorry, this is not silicon, this is this epsilon of Z and O times the field of Z and O has to be equal to epsilon ox times the field in the oxide. So it is simple as that. So E of Z and O is simply 8.5 and the field is 0.829 into 10 to the power of 5 divided by E ox is 4 times epsilon ox is 4 and this gives us E ox. So it is simply 8.5 times 0.829 4, so it's 1.76. So the option which matches our results is, which is closest to our results, is this. We got it to be 0.83 and 1.76. Okay, so we will go with option B for this thing. Okay, now moving to this problem, from which we kind of deduced that how does this substrate doping change the semiconductor work function, and we found out that the semiconductor work function, this threshold voltage decreases with the decrease in the doping, because EI minus EF has decreased, and as a result of that thing the phi f also decreased. Okay, so now moving towards this problem, which is also associated with this p-type semiconductor bar, and in this case this material, this is the band diagram given for that material, and it has a band gap of 1 electron volts, and a student was asked to fabricate a MOS using the semiconductor such that it has the following parameters, that is VTH is minus 0.16, Cox prime is, that is oxide capacitance per unit area, is 100 nanofarad per centimeter square, work function is 3.87, and also there are no oxide charges. Okay, and if the voltage across the fabricated device is VTH, what is the magnitude of the depletion charge per unit area? Okay, so we need to find the Q dep prime. This is to be found out. Okay, now from this figure we can say, we can clearly see that this psi s is equal to this chi, okay, plus Eg by 2 plus Ei minus, sorry, EFS. Okay, Ei minus EFS. It's simple. Okay, this is our psi. Yes. Okay. Now we know we have been given the value of Ei minus EV to be equal to 0.5. Okay, since this EC minus EI is zero point 0.5, EI minus EV will also be 0.5 because the band gap is 1 electron volts. Okay, now let us do some manipulations. Let us say that this is EI minus EFS, that is I am subtracting EFS and also adding this EFS, so it is EFS minus EV, it is 0.5. So clearly EFS minus EV, this thing is zero point 0.2. Okay, look into the figure, it is 0.2 electron volts. Okay, so it is 0.2. So EI minus EFS is simply 0.3. Okay, we got this thing. Now the psi s is simply chi. Chi is the electron affinity and it is 4, and Eg by 2 is 0.5, and Ei minus EFS is 0.3. So psi s value is 4.8. Okay, psi s value is 4.8 volts. Now we know the threshold voltage is simply given by VFB plus this psi s, sorry, this psi s plus Q dep prime by, okay, but there is one more condition, that is oxide is charge free. Okay, it means that VFB is simply equal to phi ms. Okay, so phi ms is simply, phi m is 3.87. okay, this is the phi m, 3.87, minus phi s is 4.8, so it is 0.93, I guess. Yes, it's minus 0.93 electron volt, so it has to be electron volts. So it is interchangeable because we know whenever we divide by q it will be volt, electron volt. Okay, these things are interchangeable, but you have to keep an eye on what you are doing. Okay, it is q times psi s here. So the psi s we got, and we have this the psi s value. Where is it? Is where it is? Here is the size. This size. Okay, this is the psi s value. Okay, so now this psi s, we have to go to the Fermi level pinning, which is at 2 phi f. So it will simply be this Vt. H will simply be equal to VFB, which is phi ms minus 0.93 plus 2 times phi f, which is 2 times 0.3. plus q dep prime by cox. Cox prime is 100 nano farad per centimeter square. So it's 100 nano. So it's 10 to the power of minus 7 farad per centimeter. So it is simply VTH. VTH is having the value of minus 0.16, I guess. Yes, it is having the value of minus 0.16. So it's minus 0.16 plus 0.93 minus 0.6 times 10 to the power of minus 7 is q dep prime. So it's simply 1.7 into 10 to the power of minus 8 coulomb per centimeter square. So it's the q dep prime value. So none of these options matches, and we will go with the none of these. Now, with reference to the previous question, what is the value of phi ms? I guess we found out, and it was minus 0.93. So the option B is the correct option to go with. Okay. Now moving to another problem. Sorry, what has happened with this? So moving to another problem, it says that we have to consider an ideal MOSFET structure with the parameters given, that is semiconductor is p-type and Cox is 1.7 microfarad per centimeter square at Vg equal to 2. It is in strong inversion, and if inversion charge density at Vg equal to 2 is this thing, what will be inversion charge density at Vg equal to 4 volts? Okay. Now using the linear interpolation for the inversion charge, so as we previously did, how does this inversion charge change? We have seen that it has some VGB dependence, that is gate to body dependence, and also the dependence on the flat band voltage and those kind of things. But these flat band extra, they will be incorporated in the threshold itself, na. Okay, so it is that thing that we can linear interpolate the charge versus we can say this inversion charge versus this uh, gate to body bias thing, and we can get the linear, from the linear interpolation we can get the threshold voltage value. So if we do that, we will be having a linear relation between this gate to body bias and the you can say the inversion charge. Okay, so if we do it like that, that is we consider this the interpolation of that inversion charge which is with respect to VGB, we can get the you can say this this size from this size versus for the QI versus you can say this VGB plot, you can get the Cox value. So actually what I'm talking about this thing. Okay, actually this inversion charge increases like this. Okay, so we can interpolate it, okay, like this, and we can say this is our Vt of, if this is our Qi prime, that is the inversion charge, and this is our VGB. Okay, this is the gate to body bias. Okay, we can say since this increases, we can interpolate it, we can use it, which we can use a straight line to interpolate it, and this thing will have a slope of Cox prime. Okay, and actually this is the interpolated threshold voltage, this is not the actual threshold voltage, so let's be careful about that. So if we use this interpolation, you can clearly see, and most of the models for the easy hand calculation use this thing, you can see that this Q inversion is simply Cox prime times the VGB minus VT. Okay, let me write it VT like this. Okay, so this is the inversion charge which we had previously seen. Now the inversion charge is having a linear relation with this gate to body bias. Okay, which is VGB, or which is also written here by the symbol VG. Okay, so now at VG equal to 2 volts, we will be having this Qi prime to be equal to 2.2 microcoulomb per centimeter square. Okay, so 2.2 into 10 to the power of minus 6 is Cox prime. Cox prime is 1.7 into 10 to the power of minus 6 times VGB is 2 minus VT. Okay, this thing will go with this, and we will be left with, so it will be simply 2.2 divided by 1.7 minus, it is 0.706 volts, which is VT. Okay, which is the threshold voltage. Now we have to find the inversion charge density at Vg equal to 4. Okay, now at Vg equal to 4, Vg equal to 4, Q inversion prime is simply Cox is 1.7 into 10 to the power of minus 6. 1.7 into 10 to the power of minus 6 times Vg is minus 4 minus Vg is 4 volts and Vt is 0.706. So it is simply, so let us multiply this 4 minus 0.706 times, sorry, 1.7, it's 5.6 microcoulomb per centimeter square. Okay, it is this value. So let us check. So the option A is matching with our answer, and we will select this option. Okay, now moving to another problem, which is, sorry, which is also associated with this MOSFET, I guess. Yes, sorry, it is associated with the MOSFET. Okay, so okay, it's one and the same thing, but it is BBS. Okay, so it's not associated with the MOSFET, it is associated with the MOSFET. Okay, so it says that we have an n channel silicon MOSFET with gate oxide thickness given by 10 nanometer, and the substrate sensitivity is found to be equal to 50 millivolts per volt at a substrate bias which is having a magnitude of 2 volts, and the Vt is the threshold voltage of the MOSFET, and we have to assume that VBS is much greater than the 2πf. Okay, that is the separation between the Fermi level and the intrinsic level in the bulk. Now we have to find out the doping concentration of the substrate from this. Okay, now for the MOSFET with the body bias given, the threshold voltage is simply Vt is simply Vto plus gamma root VBS plus 2πf minus root of 2πf. Okay, so the dVt by dVBS is simply gamma by 2 root of VBS plus 2 phi f. Okay. Also, we have been given that is VBS is much greater than 2 phi f. Okay, so this is the other condition we have been given. So from this we can say this, no, sorry, this tau Vt by tau VBS is simply gamma by 2 root VBS. Okay, yes, I guess this is correct. Okay, now if we do one thing, what do we need to find? Okay, we need to find the substrate doping. Okay, so for that let us do some calculations first. Okay, VBS is 2 volts, dVt by d this thing dVBS is 50 millivolts, 50 into 10 to the power minus 3 into 2 VBS is root 2 times gamma. This is equal to gamma. Okay, if we now multiply this with this, it will be 100, it will be 0.12. Okay, it will be 100, 100 will be 0.1, it will be 0.1 root 2 is equal to gamma, and gamma itself is equal to 2q epsilon s Na by Cox prime is equal to 0.1 root. Okay, now square, we have to square on both sides. Squaring on both sides we obtain okay, we will obtain Na, sorry, we'll obtain Na to be equal to Na will be equal to 10 to the power of minus 2 times 2, yes, times Cox prime, which is epsilon ox square by T ox square, okay, by 2q epsilon s by 1 by 2q epsilon s. So this 2 and this 2 will go, and it will be simply this will simply be 10 to the power of minus 2. Relative permittivity of oxide is 4 and for silicon it's 12, so it is this will be having just one 8.85 left, 8.85 into 10 to the power of minus 14, because one epsilon naught will go with this epsilon s, and epsilon ox is 4 square divided by 1.6 into 10 to the power of minus 19, and epsilon s is 12. T ox square is 10 nanometer, which is 10 to the 10 into 10 to the power minus 9, so it is simply 10 to the power of minus 6 centimeter square. This is the value of the Na. So let us put the values. Okay, so it will be simply 7.375 into 10 to the power of 15 Na. Okay, so option C 7.37 is matching with our answer, so we will select that option. Now again moving to some problem associated with the MOS cap, which says that an ideal MOS cap has been doped with boron doping concentration of 10 to the power of 15. So it means that uh, they uh, we are doping it again p type. Okay, so it means that thing only. Okay, and we apply a gate bias and a depletion width of 0.5 micrometer is formed with a channel surface potential given to be equal to 0.2 volt, given that epsilon naught is having this value farad per centimeter, and the relative permittivity of silicon dioxide and silicon is 12 and 4. So what is the peak electric field in the oxide region? Okay, it is similar to the problem we solved previously. Okay, the electric field is simply dE by dx is minus q times Na by epsilon s. So it's simple. Okay, so electric field is simply minus q times Na by epsilon s x minus xt. Okay, so this is the at the electric field will be maximum at the interface, and like what we drew previously. Okay, this is the oxide, this is the depletion width inside the material, which is let us say this is p type. Okay, p type boron dope. Okay, boron dope p type silicon. Okay, and this is our oxide, this is our oxide. Okay, now this will be the depletion width xt, this will be the maximum field es, and the area under this curve, will give me the surface potential. It'll actually give me the potential, and for the maximum thing we will get the surface potential. Okay, so this is our surface potential expression, and maximum electric field will be at, okay, the maximum electric field will be at x equal to 0. So es, which is at the interface, es max is simply q times Na xt by epsilon s. Okay, as simple as this. Yes. Okay, so the psi s we have got. Yes, we have got the psi s value. Yes, it is 0.2. And what we have got again, uh, we have got the depletion width value as well. Okay, we have got the doping value as well. Okay, we have got the epsilon s value, we have got everything. Okay, so the es is simply equal to 2 times psi s by xt, and 2 times psi s is 2 into 0.2, and xt is 0.5 into 10 to the power minus 6. So let me write it in micrometers only. So it is 4 by 5 volt per micrometer. This is es. Okay, now we know epsilon s times es is epsilon ox times eox. Okay, so it will simply be epsilon s is 12, I guess. Epsilon s is, yes, it is, sorry, it is 12. So it's 12 times epsilon uh, es is 4 by 5, 4 by 5 volt per micrometer. Epsilon ox is 4, I guess, yes, and this is our eox. So this thing will go with this, and we will be left with 2.4 volt per micrometer is our EOX. Okay, so we will select option B. Okay, yes, that's fine. So I guess that's all about MOSCAP I wanted to show in today's lecture. But let's get some kind of a let's recapitulate all the things that we studied. Okay, first of all, we started with the threshold voltage equation, and we solved this problem where we were asked to look into the threshold voltage of a MOSFET, and we observed that the threshold voltage, when it is oxide free, oxide is charge free, it is equal to simply phi ms plus 2 phi f plus gamma root 2 phi f. Okay, considering the Fermi level, sorry, the surface potential has been pinned at 2 phi f. Okay, so we found out from this that the VTH is equal to minus 0.32 volt. Then what we found out, we looked into the relationship of this SIS and the VGB, and we found out that it almost is follows the linear path initially, and then it saturates with VGB. Okay, it saturates with VGB at some value which is psi 0. Okay, and we found out the depletion width, it has a dependence, square root dependence on psi s, and as a result of that thing, the depletion width also increases initially with the applied bias, and then it saturates kind of, and it starts at the flat band voltage, because before flat band we will be having accumulation only, and after the strong inversion has been achieved, we will be having this spinning of this potential, surface potential, and we will be having the depletion width to be saturated at a particular value, and this almost has a square root kind of a graph. Okay, you can always check the let's say internet for these kind of things, and you will see that the square root of x also has a similar kind of a graph. Okay, so then we looked into a problem where we were given two substrate dopings, and for a substrate doping for a material with substrate doped less than the case when it was highly doped. So there were two conditions when Na1 was greater than Na2, and as a result of that thing, we observed that the threshold voltage decreases, and as a result of the decrease in the threshold voltage, the CV curve shifts left. Okay, then we looked into the problem which is associated with the electric fields, the peak electric fields inside the uh, semiconductor, which was oxide semiconductor, and we found out that it is kind of this, since the charge profile is linear, the electric field, we start from the Gauss law, and we found out that the electric field profile will look like linearly decreasing. Okay, with the depletion width, with electric field going to zero at the end of the depletion region. Okay, so we found out the value for the depletion region, and then we looked into this energy band diagram, and from that we found out the electronic the electron from the electron affinity and the band gap values, and the we found out the semiconductor work function, and we used that to obtain the threshold voltage, and the threshold voltage was given to us actually, and we from this we found out the depletion charge which will be present inside the semiconductor, considering that oxide is charge free. Okay, then what we did is we plotted the inversion charge with respect to the gate bias, and we found out that if we interpolate it using this inversion charge using a straight line, it cuts the x axis, that is the gate to body bias at some voltage which is given by the name of threshold voltage. And we found out that the inversion charge will thus have a slope of Cox prime, and it will be linear, having linear dependence on the VGB. So using this model, okay, linear, we observed that we will be having linear relation between the inversion charge and the gate to body bias. And from this, first of all, we found out the threshold voltage, and then we found out the inversion charge per unit area at some other bias. Then we looked into the sensitivity, the threshold sensitivity of this this N channel MOSFET, and after that, what we did is we solved for the peak electric field inside the semiconductor, and similarly we obtained the peak electric field inside the oxide. So I guess that's all about MOSCAP from my side. And as we have these recordings always available, and the person who had emailed me regarding the problems, I have done almost all the problems mentioned by them, and they can check the video if they, I guess they didn't join, they were not able to join today's session, so they can always check the video, and uh, try to solve those problems. First of all, try to solve those problems by themselves, but if they are not able to solve again, but I just wanted to suggest that they should just take few hints or the few initial guesses from the video, and then try to solve the problem by themselves. But if they are not able to solve the problem by themselves, then they can look into the video completely. But I would suggest them to solve the problem by themselves at first. And also, if you have any query regarding the uh, submitted assignments, the assignments that have been submitted, and the deadline has been, and the deadline is complete for all those assignments, we can always discuss those problems, and we can discuss those problems in the live session. So I guess there are no questions from your side, and the MOSCAP, I guess the problem session is we have covered almost all the problems associated with this MOSCAP. So I guess we should end the session, and let's meet in the next live session. Thank you.